as we move out away from the Earth, as we've seen, equal changes in our potential energy take longer and longer because, at least if we actually, I should say they take further and further. We've got to go further and further, and if we're moving at a constant velocity, they take longer and longer. This is simply because the strength of the Earth's gravitational pull is less and less. We've got to do less and less work per unit of distance. Now here's some calculus, and if you're not in the calculus-based course, you can just sit back and appreciate this, but you don't have to know it or understand it. You should watch it though. Okay? The total potential energy we need to get out to radius r, starting at the radius of the Earth, we get by adding up all the potential energies. And we've done this. We've added up potential energies, approximate potential energies over different distances. This integral sign is really an elongated S. It means we sum these things up. We add them up. So between the radius of the Earth and the radius r, we're adding up our f of r, our force function, times our dr, which is our distance. So we're just adding up force times distance, which is work. And of course that's going to give us our change in potential energy as we move away from the Earth. Now our f of r, recall, is 9.8 meters per second squared times re over r quantity squared, multiplied by the mass. Mass times acceleration. This is the acceleration here, and we multiply it by the mass to get the force, and we multiply that by our dr. Now, there's no calculus in this. All we're saying is we're summing this thing up and we're summing this thing up. The only thing about calculus is the notation, but we haven't done any calculus yet. Now we do the calculus, and this is where we just wave our hands. Anybody who's taking calculus realizes that we can factor out everything but the 1 over r squared here. And when we do, we get m times 9.8 meters per second times re squared, and everybody can see that. You factor that out of a sum where it's a common factor, and it factors out. Now, you're left with this integral from re to r of 1 over r squared dr. And any calculus student that has learned to do any differentiation and integration at all will be able to tell you that what you get when you do that integral is 1 over re minus 1 over r. And calculus is just a series of tricks that allow us to see what the sum would be if we summed it over infinitely small intervals. This is then our potential energy change from the radius of the Earth to radius r. Now, how much potential energy change would we have if we wanted to go all the way to infinity? We couldn't actually get there, of course, but we could theoretically get enough kinetic energy that would carry us all the way to infinity if we had enough time. Okay, so we can calculate the change in potential energy from a radius r to infinity, and we can set up the same kind of sum, the same kind of integral, and calculus students should do that. If we do that integral, we get the result m times 9.8 meters per second squared times re squared over r. Now that's just like what we got down here, m times 9.8 meters per second squared times re squared, except we have two things here. When we integrate to infinity, one of those things will be 0 and the other is going to be r, and this is what we're left with, and calculus students will understand that. Everybody else can just accept it. This is an expression for how much potential energy it would take to get us all the way to infinity from the surface of the Earth, from distance r from the surface of the Earth. Okay, so if we're at the surface of the Earth, of course, this would be re, and we just have this times the radius of the Earth, and that would give us potential energy. If something falls from very, very far away, which is practically like falling from infinity because there's not much potential energy out there past a certain point, the change in kinetic energy falling from rest from infinity to radius r is what? Well, it's a change in negative of the change in potential energy. The potential energy is going to decrease. Now remember, the potential energy out there was m times 9.8 meters per second squared times re squared over r. So that the potential energy decrease would be the negative of this, and the kinetic energy then would gain this much, which would be just the same expression, and that would equal our 1/2 mv squared, our kinetic energy. Well, we can easily solve that By solving for v, we get v is the square root of 19.6 meters per second squared times re squared over r. Okay? And that's the velocity that we need to completely escape the Earth's gravitational pull. And we call that escape velocity. So there's the derivation of escape velocity, with all the calculus thrown in case you're interested. But if you're not a calculus-based student, you can just accept those results. But accept this result, set it equal to 1/2 mv squared, and this is what you get, and you need to understand that.